Good afternoon, dear colleagues. Your attention is presented with a report on the topic, Justification of the Design of the Heat Network, based on the simulation of hydraulic modes when connecting consumers. The trend of today is the construction of new microdistricts of cities. In large cities, the central parts are densely built up and new construction is often carried out on the outskirts and territories adjacent to cities. A necessary condition for construction is to ensure the creation of communal infrastructure, in particular, a heat supply system. Existing master plans for urban development are long-term and consider a period of time of several decades. Territory planning projects take into account development in the short and medium term. The problem arises of synchronizing the development of the heat supply system with the construction of new buildings. The heat network is a complex and expensive construction project, and it is difficult to attract investors for the implementation of long-term projects. A number of existing heat supply systems were built without considering the development perspective. A multivariant problem arises about the optimal development of the heat supply system. Similar tasks need to be solved within the framework of creating heat supply schemes for settlements. Not only the investment component of the initial project depends on the correctness of the decision, but also the operational component, which is borne by energy consumers in the form of a tariff for thermal energy. Most current research papers do not consider the prospect of operation during the design life of the network. According to a number of authors, a cost-effective solution without considering the time perspective is not optimal. The development area with residential buildings in the city of Tambov is considered. The general plan of the construction area is shown in Figure 1. According to the development plan of the area, residential buildings with the designation 2K1, 2K2, 2K3, 4K1, 4K2 fall into the first place of construction, the second 6K1, the third 6K2, the fourth 6K4, the fifth 6K3. The first stage of construction has already been implemented, and without taking into account the prospects for development. The remaining stages of construction are expected to be implemented one per year. According to the calculations, the total thermal power for the subsequent stages of construction is 4.204 megawatts. Compared to the first stage, the load should increase by 74.8% over the entire construction period. Estimated water consumption for the heating network of the first stage of construction is 240.7 tons per hour. The total water consumption for subsequent stages of construction is 180.85 tons per hour. Thus, the consumption increases by 75.14%. It is necessary to connect all subsequent stages of construction to the heating networks of the existing configuration of the first stage of construction. Water heating networks were designed for prospective development under the condition of fluid movement in the area of a developed turbulent regime, as is customary in direct hydraulic calculation. When new consumers are connected to the existing network, the speed of water movement and pressure loss will change. Modeling of the hydraulic regime of the heating network of the first stage of construction was carried out when connecting new buildings. With an increase in flow rate and a constant diameter of the pipeline, the velocity of the liquid will increase. During the direct hydraulic calculation, the network was designed to operate in the region of a developed turbulent regime, therefore, the same regime will be maintained with an increase in flow. In this case, the Prandtl-Nikuradze formula can be used to calculate the coefficient of hydraulic friction. Formula 1. Figure 2 shows the results of calculations of the change in water velocity for sections of the design pipeline of the heating network of the first stage of construction, with an increase in water consumption associated with the connection of new buildings. It follows from Figure 2 that when all consumers are connected, the speed of water movement in the first hydraulic section will increase from the initial value of 1.344 to 2.336 meters per second. In the fourth section, the speed will increase by 4.24 times. An increase in speed will contribute to an increase in the values of specific head losses in the hydraulic sections of the network, shown in Figure 3. The most significant specific head losses will increase in Section 4 by 18.84 times. The smallest increase will occur in Section 2 by 3.9 times. The total pressure losses shown in Figure 4 also increased, to the greatest extent in Section 4 by 6.24 times. To change the water flow in order to provide consumers with the calculated amount of heat at constant diameters, it is necessary to increase the pump drive power, which can be determined by Formula 2. The results of calculating the power expended for transporting the coolant while maintaining the diameters of the first stage of construction unchanged are presented in Figure 5 in the form of curve A. From Figure 5 it follows that the power costs when connecting all consumers will increase by 20.4 times. Curve B in Figure 5 shows the results of calculating the power expended for transporting the coolant under the condition of reconstruction of the first stage heat network. A variant of reconstruction of the heating network with an increase in the diameters of pipelines was considered in order to reduce subsequent operating costs for pumping the coolant. Modeling of the hydraulic regime was carried out when connecting from 1 to 4 buildings and diameters were determined that provide the recommended water flow rates and pressure losses. Commissioning of new buildings is carried out at the rate of 1 per year, and the network is planned to be reconstructed only once. In this case, the reconstructed network will operate for 4 years in the mode of reduced hydraulic resistance. As calculations have shown, during this period, in a number of sections of the network, fluid movement will be observed in the transition region of the turbulent regime. In this case, the Colebrook-White formula was used to find the coefficient of hydraulic friction. Formula 3. Table 1 shows the network sections to be reconstructed. The values of outer diameters, wall thickness, section lengths are indicated in one-pipe terms. To determine the economic feasibility of the considered approaches to the prospective development of the heating network, the cost of the options was determined. Taking into account the reconstruction of the heating network, the cost of electricity for 10 years, the replacement of the pump, the total cost will be 25.8 million rubles. For 30 years of operation, the cost will be 30.17 million rubles. This can be seen in Figure 6. It follows from Figure 6 that the cost of increasing operating costs associated with pumping the coolant while maintaining the original diameters will become equal to the costs of reconstructing the network with an increase in diameters in the 19th year of the system operation, after 18.5 years. With the standard service life of the heating network of 30 years, it is economically feasible to reconstruct the heating network. The data obtained also indicate that, given the existing standard service life of thermal water networks, it is expedient to build, taking into account the prospective development of the region. It is also advisable to carry out the reconstruction of existing networks of small length with an increase in their throughput. The cost of pumping a coolant with large hydraulic losses after several years of operation begins to exceed the cost of reconstruction. The longer the standard service life of the equipment, the more effective the measures to increase the throughput of the heating network. Slide 7 presents the conclusion of the work. With your permission, I will not read it. Thank you for your attention. The report is over.